It sounds incredibly sophisticated. Overlay, transport, virtualization. And once again, we find intermediate system to intermediate system routing coming to the rescue to solve issues at layer 2. In this particular nugget, we'll quickly review OTV technology and then roll up our sleeves and see key commands and key things that could go wrong from a troubleshooting perspective. What's in a name? Well, in the case of OTV, quite a bit. We have overlay. The overlay concept means that OTV is going to provide an overlay virtual private network on top of an existing IP network. It's totally independent of the underlying infrastructure, technologies, and services we are utilizing. As long as that network is capable of transporting IP packets, then OTV can do its magic. Transport indicating that we are going to take our layer 2 traffic from a data center and we are going to transport it over that layer 3 network seamlessly. So we have fast convergence, load balancing, multicast replication. It can leverage all of the underlying capabilities of the layer 3 transport network. And again, it's moving that layer 2 traffic to the other data center. Remember the theme here that we are moving towards data centers that are massive layer 2 infrastructures instead of more complex layer 3 networks. Then there's virtualization. Virtualization comes from the concept of OTV providing virtual multi-access to these layer 2 sites. It can move unicast, multicast, and broadcast traffic, and we don't need to go and provision each remote site every time we add one with connections to all of the other sites. It is done without virtual circuits, pseudo wires, or any type of point-to-point connection maintenance between the sites. Now, what really makes OTV shine is two real fundamental principles here. Number one is the dynamic encapsulation of our layer 2 frames. So it is a point to cloud type model where the layer 2 frames are going to be encapsulated in IP packets and then independently routed thanks to ISIS to the particular destination or sites to which they are destined to. Then there's the concept of protocol learning. Overlay transport virtualization is going to use MAC address routing based on the ISIS protocol to dynamically learn which MAC addresses are available in each of our layer 2 connected sites. So unlike Fabric Path, it's important for us to remember that OTV is an edge function. Layer 2 traffic is going to hit our Nexus device at the edge of the network, and it's going to be dynamically encapsulated, as we said, in those IP packets and then sent into the cloud, the IP network, and then delivered to another edge Nexus device at another site. The OTV edge device can either be in the core or aggregation of our Nexus 7000 base data center. A site can have multiple edge devices, and when we do this, we obviously add nice resiliency of being able to get our traffic out of our data center to another one, and we typically call this multi-homing. By definition, an edge device has interfaces that are connected to the transport network and interfaces that connect to the layer 2 switch network. The layer 2 interfaces that receive the traffic from our VLANs that are being extended across the OTV network are called internal interfaces. So these are our internal interfaces. They're regular layer 2 interfaces, and typically we would use 802.1q trunks there. What's interesting is no special OTV configuration needs to be done on those internal interfaces. Now there's the concept of a join interface. The join interface is used to source the OTV encapsulated traffic and send it to the layer 3 domain of the data center network. The join interface is a layer 3 entity, and it can only be defined as a routed point-to-point physical or logical port channel interface. An OTV overlay can only have a single join interface per edge device. Multiple overlays can share the same join interface. The overlay interface is a logical multi-access and multicast capable interface that must be explicitly defined by the user. The entire OTV overlay configuration is applied on this logical interface. So, our edge devices, and then we have our internal interfaces connected to our layer 2 domain, then the join interfaces, and then we have the logical concept of the overlay interface. So those are the main ingredients of an OTV infrastructure. Now remember, in order for this to work, these different edge devices need to be able to discover each other. We call this neighbor discovery and adjacency creation. It can be done in one of two ways, as you recall. If the transport's multicast enabled, then we can use a multicast group in order to exchange the control protocol messages between these edge devices running OTV. If we don't have a multicast enabled transport, then we have to configure the adjacency server to which all the other edge devices are going to register. The adjacency server will then communicate this list of devices belonging to a given overlay to all of the other OTV edge devices. Cisco strongly recommends that we consider a multicast enabled transport in order to easily extend VLANs between the different data centers. What about spanning tree protocol? Well, sure enough, spanning tree protocol, I'll draw it here as part of this data center. So this is data center 1. Spanning tree protocol could be running in here. That's fine. But it is absolutely going to be blocked from transmission over the OTV devices. So this is built into OTV and requires no configuration. This dynamic blocking of BPDUs from the internal interfaces going into the overlay. Sure, again, you can run STP in here, but it is absolutely not to be transported over the overlay network. This is a really nice feature, separating our spanning tree domains and limiting any particular problems that might occur in one particular data center from affecting another. Now, one thing we really love too is this multi-home and load balancing configuration that's really simple to pull off. Let's say this is data center 2 over here, and we have Nexus A and we have Nexus B. What we end up doing is multi-homing here for these OTV edge devices. This adds redundancy, and it really is a wonderful configuration. OTV has a built-in mechanism to ensure that only one of these edge devices forwards traffic for a given VLAN. The edge device that has the active forwarding role for the VLAN is called an authoritative edge device, or AED, for that particular VLAN. The AED has two main jobs. Obviously, forwarding the layer 2 unicast, multicast, and broadcast traffic between the sites, and advertising MAC address reachability information to the remote edge devices. The AED role is going to be negotiated on a per VLAN basis between all the OTV edge devices belonging to the same site. To decide which device should be elected as an AED for a given site, the OTV edge device establishes an internal OTV control protocol peering. The internal adjacency is established on a dedicated VLAN named the site VLAN, and this particular VLAN is used to negotiate the AED role. The site VLAN should be carried on multiple layer 2 paths internal to a given OTV site in order to increase the resiliency of the internal adjacency. It's interesting to note, of course, as its name implies, this site VLAN is not carried into the OTV network. Now, when I troubleshoot OTV, I really find myself following a process that's very similar to troubleshooting a routing infrastructure. By that, I mean I make sure the control plane is built beautifully, and then after that, and only after that, I would go ahead and examine the data plane functionality. So, in other words, you might make sure your adjacencies are established fine. Make sure that the MAC addresses are being learned properly on the edge device. Then we could make sure the MAC addresses of the sites are being advertised properly by OTV. And then finally, you can actually see if the traffic forwarding is functioning normally across the OTV infrastructure. So obviously the great news is that Cisco provides us with very simple, straightforward, powerful commands that we can utilize to verify each aspect of like the control plane behavior. Here you can see show OTV adjacency. This confirms that a neighbor relationship has been established across our OTV network. Remember, OTV adjacencies are established using typically our configured multicast control group. If they're not establishing, we can verify the state and configuration of our overlay interface, and we can also confirm that IP multicast forwarding is indeed functioning within our transport network. Now, should you not be seeing the adjacencies that you expect to see, a great follow-up command would be show OTV overlay and then your overlay number. Notice that this is going to really give us two pieces of information that are absolutely key. The VPN state as well as the particular control group that we are utilizing. So we want to see a VPN state of up, and we want to ensure that the particular control group matches exactly what we would expect to see for our multicast control group. Now recall another great step is to verify MAC address learning. You can use the show OTV route command as we see here to see all the MAC addresses that are learned for the extended VLANs. Notice we see both local addresses that were learned on the internal interfaces and remote addresses that were learned through the overlay. This show OTV route command is only going to show us the MAC addresses for VLANs that are extended on the overlay. If a MAC address is shown in the show MAC address table command for a VLAN on an internal interface, but the show OTV route command does not show the address, then you should verify that the VLAN was added to the list of extended VLANs for your particular overlay. So remember, after we verify control plane mechanisms, we verify the data plane forwarding. In order to verify packet forwarding, I like to use show interface overlay. Notice this is a very direct way in order to verify packets sent and received over our overlay interface. And finally, we do have some additional OTV verification commands I'd like to share with you. Like, for instance, show OTV statistics. We have a multicast and an overlay keyword we can use here in order to see specific statistics regarding the OTV control plane protocol. There's show OTV ORIB clients. This displays information about the OTV routing information based clients. And then finally, show OTV site, which displays information specific to our overlay transport virtualization site. By the way, if there is any issue in establishing an OTV ISIS adjacency, something else we can do is look at the ISIS adjacency log. You would do this with show OTV ISIS internal event -history adjacency. So this command is a mouthful, but this will allow us to see the adjacency log and perhaps track down problems. Now, let's talk about first hop redundancy protocols in OTV. This is a messy situation that we could run into. Over here we have site B, and over here we have site A, and we've got these edge devices. For a particular VLAN, let's say this is the HSRP standby device, and over in the other site is the active device. Sure enough, what could happen is traffic could enter, be routed through the OTV environment to the, not an all-terrain vehicle, but the overlay transport virtualization. It could be routed over to this active HSRP, let's say, device, just to be routed back to site B. So this is a very suboptimal situation that could result from a first hop redundancy protocol like HSRP, VRRP, GLBP, any of them. So we want this behavior to be prevented, since it is at the very least going to lead to quite suboptimal routing. So what is the solution that I want you to be aware of? Well, in OTV we call it first hop redundancy protocol filtering. You got it. So what we are going to do is filter the first hop reachability traffic so that the different routers and the different sites don't see hellos from each other. So what we're going to get is we're going to get the active and the standby elected in each site so that it doesn't cross the site boundaries. If the routers in the different sites don't see hellos from each other, they'll of course select an active and a standby in the particular site. The active router in the site will be responsible for forwarding the traffic for the virtual IP and MAC address for that particular site. Now, to filter the first hop reachability traffic, we need to do two steps. First, a VLAN access control list, that's a VACL, is going to be implemented in the OTV edge device to block the FHRP hellos and prevent them from being forwarded on the overlay. Second, the virtual first hop redundancy protocol MAC address should not be announced to other sites as it normally would. This can be achieved by implementing an OTV MAC route filter. So we have our VACL as step 1. As step 2, we have our OTV MAC route filter. These are the 2 steps you need to be aware of that we would engage in for the first hop redundancy filtering. So as a bonus here, I'm going to include in the Nugget Lab files a presentation for you called Overlay Transport Virtualization Best Practices Guide. This is from Cisco. You're going to absolutely love reading this cover to cover. And if you look down on slide number 23, you'll see there's a full-blown configuration example for you of the first hop redundancy protocol isolation that I discussed. And you will see, in fact, let's go down and take a look at it. You will see the 2 steps clearly spelled out for you from a configuration standpoint. There is step 1, the configuration of our VLAN access control list. And then if you scroll down, you'll see step 2, the application of a route map to the OTV control plane, intermediate system to intermediate system. So I will include this particular document for you in the Nugget Lab files. In this nugget, we zeroed in on the overlay transport virtualization technology that we can utilize in order to connect seamlessly data centers from a layer 2 perspective with a little dash of ISIS routing intelligence thrown in for good measure. I sure hope this nugget was informative for you, and I'd like to thank you for viewing.